Page down. Okay. Sure. So what I'm going to talk about first, soils and regolith. We'll visit Earth briefly, over the moon. This is a new bit I didn't have time to talk it back in February with. It's a little bit about asteroids, and we'll end with Mars. Okay. I'll keep hitting the right button, and I got my little button here, it's helping me. So, soils 101. This is, when you go to soil science school, this is what they teach you in terms of formation factors for soil. This gentleman, Hans Jennings, back in 1941, came up with these 5 main factors that cause the creation of soil. Parent material, which is material it forms from. It could be bedrock that breaks down, or sediment that's been blown in, or sediment that's been deposited by water. But some material where it kind of all starts from. Relief, which is your topography. The upper topography or the lower topography has an effect. Climate, of course. Organisms, mainly soil microorganisms. Gophers are involved as well, and earthworms. And of course, time is an important factor because to form soil, it takes a long time. And in his function statement, S being a soil property equals the function of these 5 main properties. But he, at the end, which I found interesting, he had 3 dots, and these are unspecified factors that may be at work on forming soils at some locations. I thought, oh, that's interesting. So soils, there are many different definitions of soil. Some are nice and short and to the point, others are paragraphs long. It's a difficult thing to describe. The other thing some people will say for the moon, there's no soil in the moon, that's what we call regolith. And there are fewer definitions for regolith, and it's a little more simple. But soil is important for many areas of study. Pedology, which is the science of soil, the study of soil, ecology and geology, of course, and engineering, and more recently, planetary science. Now, basically, you have what we call the regolith. I'll give you a definition of the regolith. And then the soil forms at the top of your regolith, basically. And in basic soil science, the soils are broken down into three main layers. A, which is usually the top, B, and then the C is what we call the parent material, which is relatively unaffected, but it probably has had some effect, and been affected over time. And this is laying over bedrock, and there's probably an aquifer down there below, and then there's the other bedrock further down. So this is kind of the from an Earth perspective, what we consider soil is. So, but the question is there any reason why we can't be calling material on other terrestrial planets soil as well? And many have felt that there needs to be a new definition for soil. So they came up with one. SSSA is the Soil Science Society of America. Well known in the soils and environmental area. We came up with a new definition of soil in 2017. So they define it as the layers of generally reduced material and or organic matter that are affected by physical, chemical, and or biological processes at or near the planetary surface, and usually hold liquid, gases, biota, and support plants. So, and or is important because many people, some will argue there is no soil on the moon because there's no organic matter and there's no biology involved. So, but that's a very terrestrial or Earth perspective. Personally, I would have ended it right here because or changes words to may. Unusual. It's true for Earth, but it certainly is not true for the moon on some of these factors. So. But anyway, they came up with a more generalized definition for soil. And for regolith is the cover of loose material overlying the bedrock of a planet, satellite, or asteroid, and includes fragmented and weathered rocks, soil, and sediments. Okay, this is just one definition. So, Okay, let's move on to our home planet. So as we know, during the Palladian eon, which is the time when the Earth formed, the Moon formed early in this phase of this eon, and it is believed that and there's a lot of, as it was forming, there's a lot of material colliding with the object that eventually became the Earth. But there's some hypothesis that there may have been a late bombardment period, either late in this eon or just past it. And there's some evidence with respect to the moon and showing the impact record from that late bombardment. Mercury would be another case as well. And plus the soil sample that came from the Apollo astronauts missions gives some indication about that this may have occurred. But there is some criticism that this may not have occurred, this so-called late bombardment. But the point is that the Earth had been impacted probably just as much as the Moon and Mercury had during that time. Well, we know that the Earth continues to receive material on an ongoing basis, not anything like the times back in that era. But in this paper, they determined that about 15,000 megagrams, one megagram is the same as 1 metric ton. So 15,000 metric tons enter the Earth's atmosphere every year, and they calculated that maybe about a third of that material ends up on the Earth's surface. So I figured, okay, how much does that contribute to our soil? So I looked up the surface area of the Earth and calculated the flux, which worked out to be 10.2 micrograms. So that's 1/1,000,000th of a gram per square meter per year on the surface of the Earth. So I'm taking some very assumptions here in terms of uniformity. But that's per year. So I said, well, what about the ages of the soil? Well, in Canada, the ages of soil range anywhere from 15,000 years since the last glaciation to maybe over 700,000 years. For example, the Cypress Hills, or the upper part of the Cypress Hills, which was not glaciated in the last ice age. So if you multiply that, it still turns out to be a fairly low number, 153 to a little over 7,000 milligrams, or 1,000 of a gram. So it's actually getting up to almost 7 grams per liter over that time period. Still, not a lot of materials being added to the surface of our soil. So in terms of an extraterrestrial source of material for soils on Earth, it's relatively small in the current period. But we know the Earth has been impacted by larger objects over the years, over the centuries. I think there's about 120 known craters on the Earth, and this is one that we are fairly familiar with, the one down in Arizona, the Barringer crater. It's 1.5 kilometers in diameter, 46-meter diameter or asteroid, what should we call it, an asteroid, entered the atmosphere 50,000 years ago and created this crater. Now, that's a fairly large object, but it would not have caused a global issue here. It would have been more of a local impact. Now, in the area that it would affect, I'm not sure what the vegetation or the animal life was like at that time. It might have been totally different than it is now. But whatever it was, the local area would have been completely devastated and changed from this impact. It certainly would have changed the soil conditions in the area. So moving on to the moon, as we all look at the moon, we can see, of course, the light and dark areas. It's been determined that on the mirrors or the dark areas, the regolith is about 4 to 5 meters deep, whereas on the highlands, the lighter areas, is about 10 to 15 meters deep. Now the
Can I
material.
just ask you a question?
Yeah.
Like, is that, I know the moon is just basically all covered with dust, but is that what we're talking about here? Is that basically dust? 4 to 5 meters down on the Mare?
Yeah, well, no, it'd be dust, it'd be probably a lot of broken rock and stuff.
Yeah,
So
it's
the loose
only
granular.
loose material.
Yeah,
And
yeah, the loose
probably
material.
from meteor impacts, right?
Yeah, break it up over time, yeah, so it'd be a
Just
granular.
wanna make sure I was understanding.
Yeah, so what I'll be talking about a little bit later is how the surface of the regolith has changed, so-called soil. So, the material, at least on the surface, is unconsolidated, so there's no sorting occurring. The bulk density, as we call it, is 1.5 grams per cubic centimeter, which is about what our soils are like. Our surface soils can be 1.1 to maybe 1.45. Water is 1, just to give you an idea. So it's very fine grained material. It's a very, very powdery material that's on the surface of the moon. 50% of it is less than 100 micrometers in size, and 90% is less than 1 millimeter in size. This stuff is electrically charged. I mean, remember looking at the Apollo astronauts on the moon, you see their nice bright spacesuits got all covered in dust, and this stuff clings to everything. The other thing, to underline this is going to be a major issue for long-term stays on the moon, is that this material is very sharp. The edges, the sharp edges on it, and very abrasive. And the astronauts, even the short time they were on the moon, of course they were concealed, enclosed in their spacesuits, so they weren't themselves exposed to the lunar surface. But when they got back into the lunar module and took off their helmets and stuff, a little bit of dust floated in the cabin, and they had issues breathing that little bit of dust that was in the lunar module after their walks. So this is going to be a major issue, how to manage the dust for extended periods of time on the moon, as what they're hoping to do is
Could it cause the same kind of problems as like asbestos fiber?
Silicosis.
it could, yeah.
Interesting.
No free water in the surface of the moon, rock fragments and breccia, and it measured less than 2% of meteoritic components in the lunar soil is foreign material, which is not surprising. So,
What is breccia?
I think it's broken up rock.
It's like solidified molten rock, I believe,
it's
right?
been broken up, yeah.
From impacts.
Okay, in terms of lunar soil samples, there is a list of what was returned by the Apollo astronauts back in '69 up to 1972. So a little under 400 kilograms have been brought back to Earth, and I believe most of that, or a good chunk of that, is still in storage, still being kept for long-term use. The Russians did bring back some through the lunar program back in the 1970s as well. And more recently, China has sent 2 probes to the landers to the moon. This was in 2020, and this was just earlier this year. They brought back a couple kilograms or so kilograms of lunar soil. So altogether, less than 400 kilograms of lunar soil has been sampled and brought back to Earth. Compared to, what's the mass of the meteorite collection that have been recovered on Earth? I said, well, I'll ask Dr. Google and see what he says. And my understanding, about 600 or so, over 600 metric tons of meteorite material have been recovered from. Oh yes, Mark?
I'm just curious with the lunar missions and the China missions that they brought back so little material. What is it? The research had all been completed, or there was just a lack of
Well, I
interest?
think they landed with these are robotic missions.
Right.
And they probably were very limited how much they could take, because they had to land on the moon,
Got it.
collect the sample, pump it into whatever part that was going to lift off and come back to Earth, and they probably was very limited to weight.
The fact that they sent anything back is actually shocking to me.
Yeah, well, it worked a couple of times.
Yeah.
I'm not sure if they had any failures. China's 2 for 2, both their missions. This was on the near side of the moon, up towards the northern part of the moon, and this was on the far side of the moon.
Is it safe to assume that like our research here has improved? Like you don't need 95 kilos to do the kind of fine-tuned research we're doing nowadays anyway. You could probably do just as much with 1 kilo.
Oh, well.
Or is that not part of it?
Yeah, well, yeah, I mean, when they do the analysis, they're just probably using milligrams.
Yeah.
Yeah, this could last for a long time. Same as these things have been around since the early 70s, the follow samples, and I'm not sure how much of it's still in storage that has not been analyzed yet.
Well, and is there use in that? Like if it's been on Earth, isn't it after a certain amount of time like contaminated with Earth organisms?
Well,
So
that's a
is
problem with potential problem with meteorite collection.
Yeah.
So that's why it's beneficial to go out and collect samples like this, because you can contain it and try to minimize the contamination. And
Yeah,
then
they're
probably
frozen in the clean room.
they're stored in clean rooms, they're stored probably under nitrogen, cold temperatures, and super clean room laboratory. There's a building, I think it's called Building 31 at the Johnson Space Flight Center, where they keep, at least Americans keep their samples, and it would be it's a super clean keep these types of samples.
How is the consistency over the moon? I'm not sure if that's an odd question. Is there a consistency right around the moon? So would a sample be the same on?
No, there'll be main gross differences will certainly from the light to the dark areas.
Got it.
And the Apollo landings, those that landed in the highlands compared to those landed in the seas, are quite different.
Mm-hmm.
And then there's, I think, a couple missions, or at least one mission is kind of on the edge, and the transition between the two,
Mm-hmm.
and they fall in between.
Got it.
So there's some. So the dark areas, the mirrors are more basaltic, high in I think it's iron and titanium, whereas the highlands are more rock-like or more basaltic, aluminum and aluminum and probably iron.
Got it.
Those are iron.
Silicon?
No,
Zinc?
it doesn't matter. It's aluminum and something else. I can't remember now. That tends to be more rich compared to the seas. So just to break down the soils, lunar soils that have been sampled by the Apollo astronauts, and I think may have contained some data from the lunar samples from Russia. But basically, the lunar surface material has 5% glass, 24% minerals, 22% of just rock fragments that have been broken up. But the interesting thing here, and it's unique for the moon, this doesn't occur on the Earth. You have about 50% of this material called agglutinates, which is a melt of glass melts, lithic or rock material, and mineral material formed together. And I'll talk more about that in a little while here. But this is an image of some particles from the surface of the moon. These are some volcanic glass, and some impact glass here. This is the mineral, probably plagioclase or something like that. Rock fragments, and I think these were agglutinates. You can see the size. It's a very fine material. So very sharp. You can see that it's very sharp material. You don't want to be.
So these samples come from, they're basically on the moon or in a rover or whatever, and they just take our shovel full out of the ground and dumping it in a bucket and off they go. Is that essentially what's going on?
Yeah, they had different instruments because it was difficult for them to bend over the ground. And then there'll be I think I got an image of them showing kind of like a rake-like device that can pick up rocks.
So it's kind of like a day
So,
range, right?
Yeah, and they tried to take cores. I'm not sure the deepest core that's taken, but they did have some difficulties in taking cores, trying to get some depth. Mainly it was surface material, rocks, and the loose soil material from the surface that they collected. And of course, getting back to Mark's question, the Apollo astronauts, they were able to collect a lot more because they had the equipment, the lunar module could launch. They could launch a lot more heavier weight. And the rover or the landers of Russia and China. Okay, one process that is often referred to as space weathering, and this occurs mainly on airless bodies such as the moon and Mercury and the asteroids. There's an astro on there. So I'm going to just talk about some of the processes that we have determined occur. One, of course, is microbombardment. So this is occurring on a constant basis. Of course, it would be much larger impacts, which would be a lot more rarer, of course. But the moon is being pelted by these micro meteorites, as well as the Earth. But most of this material gets burned up in the atmosphere, and the moon really doesn't. So it impacts the surface, and it causes melting, vaporization, and of course, just the shock, because these things are traveling in big clips, so they can fracture material on the moon. And this leads to contamination from whatever material that survives the meteorites or gets mixed into the solar surface. It's the one called agglutination, which is just a breakdown of larger particles into smaller particles. And again, this agglutinate formation occurs. You get this melting, creating glass, and rock material gets solidifies, and rock material gets mixed into with melting glass. And these agglutinates, they're very porous. You know, kind of like air bubbles or not air bubbles, but it's very porous material. Of course, there's lots of radiation, cosmic rays, solar wind, UV, visible, and some of these high energy cosmic rays can etch the surface of particles. So kind of slowly over time breaks down particles. Of course, thermal cycling, because of course with the day to night of the moon is extreme temperatures, almost as extreme as Lethbridge. Actually, it's a little more extreme. So going from I think minus 130 to a plus 120. So the rock fragments will start to break down with those stresses. And this process called sputtering, where the radiation and possibly some impacts can cause, at the atomic level, materials being ejected off the surface. Some of it could escape, particularly on asteroids and whatnot, but a lot of it gets deposited back onto the surface of other particles nearby. So you get this kind of resurfacing occurring. Sublimation in volatile material escaping, and of course mixing, sometimes referred to as gardening. So just over time, because you have to realize, you have to appreciate the time scales here. Remember that one factor of soil formation, time? So we're talking about millions and millions of years for this process to occur. Of course, a large asteroid hitting the moon causes sudden change, of course. And the last thing I think I want to talk about this process that occurs on the moon. It's called the creation of nanophase iron, and this has been an important process that has occurred. This does not occur on the Earth. So what happens, particularly with the bombardment, and I think also with the solar wind, there's a lot of hydrogen that gets absorbed onto the lunar surface, and when you have these impacts occurring, this hydrogen can get released and creates what we call a reducing environment. And iron oxides, what this causes, the hydrogen will strip the oxygen off the iron and create free metal iron, water vapor. And it's this free metal iron that gets accumulated in the lunar surface and in those agglutinate material and on the edges and on the surface of the particles as this process occurs.
Barry, is there an alchemical process that we can learn from that creates a byproduct that we would typically see in some form of a chemical makeup of sorts from that?
Makeup of what?
So for example, like from what we can learn from that, is there a natural byproduct that we can see or experience, whether it's in manufacturing or the merging of chemicals, or even just the byproduct, the creation of iron, for example?
Yeah, well, that's right. you might think, you could suggest that ostriches might be an easy source of iron if they're gonna ever mine the moon, which I
Right.
hope they never do.
Mhm.
But, but there's talk about mining asteroids and the moon. But, anyway, but that could be
Yeah.
they say this could be a source of iron. Yeah, for sure. Okay, in terms of the lunar soil that gets generated over time with all this bombardment and radiation and all those other chemical processes occurring, they can measure how mature the soil is on the surface of the moon by measuring the glutamate content. As it gets higher, it's an older soil, it's been on the surface longer. Grain size, so as the grain size gets smaller, it's an older soil. Density of those cosmic ray traps on the surface of particles. Implantation of solar rare gases, as that increases, that's an older soil. The formation of that iron, of metallic iron. The depletion of volatiles, the rock material, a number of rocks on the surface. So if you see an area that has very few rocks, it's probably an old layer because all the rocks have been broken down from all these processes. So on the lunar surface, there's this process in terms of a balance between destruction and construction that's occurring. And this gives you an indication of the maturity of the soil. And now, unless there's a large impact nearby, where you get material thrown out of a crater and covers the soil, the old soil, then you'll get in that case, you get a new surface, material that's been unweathered further down, been ejected from the crater and then spread over the surface. And then the whole process starts over again. Okay, moving on to asteroids. In terms of missions to asteroids, there have been several. Some have been purposeful-based missions to asteroids. Others have been just in flybys from other missions that are on the way to another. For example, Galileo, on its way to Jupiter, it flew past. I think it was actually Casper, if I remember right. But anyway, there's been 15 flybys of asteroids. There's been 6 orbiters, 5 missions have landed or impacted asteroids, and there have been 3 soil sample returns or surface sample returns from asteroids. And this is Arakawa from Hayabusa in 2010, Urugu from Hayabusa 2 in 2020, and most recently, asteroid Bennu from OSIRIS-REx, and it returned its samples just late last year. I think it was October, I believe. And these first years are the years that the missions were launched, and the latter years are the years that the samples were returned. So it takes a long time to get a sample. Now I'm just going to focus on Bennu, the most recent one. So Bennu, OSIRIS-REx was launched in September of 2016. It went into orbit around Bennu in 2018. I think it was in December. And it stayed in orbit for a little over 2 years. Collected its sample, left orbit, and it deposited its sample in September of last year. And it collected 121 grams, so just a little over 121 grams was collected by this mission. Now, it's interesting that after the spacecraft flew past the Earth, it dropped its payload capsule, the spacecraft was renamed OSIRIS Apex, and it's now on its way to Apophis, the asteroid Apophis. And I believe it's going to rendezvous with that asteroid shortly after it makes its closest approach to Earth. And it's going to stay in orbit. I think the plan is for 18 months around Apophis, and then more about it.
So that encounter will be 2029 then?
2029,
Okay.
yes, that's when it occurs. So Apophis, we don't know, so one is an asteroid that's going to pass extremely close to Earth. I think it's going to become even closer than our geostationary satellite. asteroids, I believe, so it's coming in pretty
You can
close.
see it during the day.
It's gonna go. So,
It'll be cloudy.
yeah, it'll be fine. So, Bennu is it's fairly big. It's 500 meters across the equator from pole to pole, no larger 500 meters. It's what they call a B-type carbonaceous asteroid, and apparently it's part of the Apollo group of asteroids, which are near-Earth asteroids in the solar system. It has a beetle of 4%, which means it's very dark. It's like asphalt, fresh asphalt. I think the moon's albedo is about 8. So the moon's quite dark, but this one is very dark. It rotates 4.3 hours on its axis. It has a density of 1.19 grams per cubic centimeter. So it has a low density. They think it's just a rubble pile. It's very loosely held together, and it's spinning on its axis every 4 hours. Now the surface density, again, remember water is 1. Our soil, if you go out to a nice loose soil with lots of organic matter, it might be around 1.1 grams per cubic centimeter, just to give you a sense. But this is the average density of the whole body. The surface density here is going to be considerably less than 1. It's very, very low density material on the surface. Now they were expecting to find it covered with fine-grained material, but they didn't. What they found was an asteroid covered with boulders of varying sizes, from small boulders up to the size of football fields. The largest boulder on this asteroid is about 18 meters high, equivalent to a 6-story building. It's a large boulder.
And it's only 500 meters across.
Yeah. Now there's a few white colored. This is a very dark object. That's because it contains a lot of organic carbon. We'll talk about that a little bit here. But they see a few bright spots, so they think these are exogenic material, and maybe other objects from other asteroids have impacted and left this material on the surface. So spectroscopically, the surface of Bennu is homogeneous, means it varies very little over the entire surface. However, when they do a deep dive in the data and do some statistical analysis, I'm not that familiar with spectroscopy, but they determined that from the data, about 89% of the surface has a kind of mean blue spectrum. About 4.5% of the surface is bluer than that and higher reflectance. 4% is redder, 2% is redder, and 0.5% is the reddest and has the lowest reflectance. And so they were able to separate this out statistically from their spectroscopic data. And I think the other thing they discovered was that so this is the equator. So if you can imagine, let's say this boulder here sitting on, you have a face of the boulder facing the equator and one side facing the pole. And we discovered that the spectrum was more blue on the equator side of the boulders as opposed to the side that's facing the polar region. And what they think is causing the difference between the spectrum is the effects of space weathering and bombardment on these boulders. So this side would be more exposed to solar radiation and bombardment as opposed to the pole-facing side. That's kind of a neat thing. And we think that the color variations from the spectroscopic analysis is due to the immuno heterogeneity and varying exposure ages. And this is a map of showing that data. The gray is the 89%, so very uniform over most of the asteroid. But the redder, what appear more red, tends to concentrate along the equator. That's kind of interesting. There's a long, latitudinal pattern here that they discovered. And the white bits is where they didn't have data, spectroscopic data for some reason. And the sample that was taken was towards the northern, I think it was called the northern hemisphere of the asteroid, was taken from this area, because they thought it was maybe a younger type of material. They wanted to get the most pristine. They didn't want material that might have been on the surface for a long time exposed to space weather. So they wanted something that was a little more pristine. So that's where they eventually selected the sample. During the process, I think they selected 4 sites and eventually selected this one, and they named it Nightingale. And that's where the OSIRIS-REx touched down and grabbed its sample. And
So I assume it's not tumbling, Bennu, it's not tumbling in space.
no, it's spinning on an axis. Yeah, every let's say a little over 4 hours.
So then Barry.
Yeah.
Because it's spinning, the red areas are where it faces the sun mostly, right?
Yeah. Yeah.
So, and it's orbiting the sun in its own orbit.
And it's orbiting the sun. More or less, it's at I think its average distance from the sun is 1.19 astronomical units. It's more elliptical than I think it goes up almost to Mars. It does cross Earth's orbit, so it's near Earth. So it is an object of concern,
Right.
but there's no concern about it impacting Earth anytime soon.
It's just gonna be a loose snowball when it hits yours anyway, 'cause it's
Yeah,
just gravel,
Yeah,
right?
yeah,
It'll be like a shotgun blast,
When I
right?
did a calculation, I weigh about 85 kilograms. If I stood on the surface of Bennu, I'd weigh less than a gram.
Right.
So, pretty like, though if I was on the pole, it'd be heavier.
Mhm.
It'd be like 0.6 grams on the pole, and the equator would be 0.5 grams or something like that. I can't remember the exact numbers, but yeah. So the stuff on the surface is just sitting there, just kind of, it's not cohesive, it's kind of a loose material. Yeah, you go up there and blew at it, it probably would blow something away.
Yeah, so if there were any impacts, it would be sort of.
And actually, OSIRIS-REx, while it was in orbit, it could see, it monitored, it photographed the materials leaving the surface of the asteroid. This is one interesting study, and it's kind of getting to more of the soil side of things here. In this study, they did an analysis of all the craters. It doesn't look like this crater, but it's probably remnants of craters. So we looked at craters of different sizes. Of course, the bigger the crater, the deeper the crater. So the surface, of course, is all the surface rock material. But when we started looking at the shallow craters, they found that there was bottom of the crater, it was fine, loose material. So it was punching through that surface rock into fine material. But at the very larger craters, and I think this was started getting up to 25, 30 meters across, we started running back into larger rock material. So what we think they've discovered is that below the surface, there is 1 to 4 meter layer of fine material. And what they think how it gets there is that as the surface gets broken down, this material slowly percolates through loose material and forms this subsoil, if you like, underneath the rocks, which is kind of interesting process that's occurring. Impacts and thermal fractures will cause the surface to break down over time. So when the samples returned last October, I think it was, or September, it took them, I think, 6 months or so to catalog. It was a very slow process. And this material is only becoming available now, like to scientists around the world, and they're planning to send samples to, of course, the United States. Canada's gonna get samples if they haven't got already. Japan, Australia, Europe, of course, and I think they're sending samples to India as well to analyze. But they did do some quick analysis right off the bat, and this is some of the things that they found. So this is the actual material. You see, this is part of the sampling there. So they found that the elemental content of this material is very similar to the soil abundance. It has 5% organic carbon, which is very high. If you want to compare it to our soils in the Lethbridge area, we're a dark brown Chernozemic soil. The surface material probably has about 3 to 4% organic carbon. So this is quite carbon rich. Hydrated clays or phyllosilicates, monofilament magnetite, carbonates are found, anhydrous hydrosilicates, olivines, and minerals, sulfides. They were quite surprised to find sulfates, and they found these things which I've never heard before. These pre-solar grains in the material, which apparently are a material that was already formed, little particles already formed before the solar system formed. So this is very old particles. Now some of this material is indicating like things they analyzed for us, these phosphates and the hydrated clays and the organic matter. Whatever parent body this thing came from had a lot of influence of water. So that's one of the reasons why they targeted this phosphorus as well as the carbon.
Okay, Barry, just so you know, we're at 43 minutes.
Okay, yeah, I'm just gonna be moving on the bars here and then we'll wrap it up. So Bennu, in terms of what there's observed in terms of what's affecting the soils or the surface of the planet, of the asteroid, is that it seems to be a mass movement of material from the polar regions, the upper higher latitudes towards the equator. Of course, like all the other earlier space splitter process I was describing, is of course large impacts, micrometeorites. This percolation of fine grains down into the subsurface, dehydration occurring, we found around the equator. It's less hydrated, and this exfoliation of fine grain material that from impacts, some material will be flying off in space, and some material will come back onto the surface. So in terms of space weathering on airless bodies, some of the factors, high-level factors, of course, location, how close are you basically to the sun, surface type, and time, and various aspects in terms of impact speed, radiation temperature, and composition, size, and texture of the surface. So let's just finish up with Mars here quickly. Just quickly overview of Mars. Of course, when I was doing this presentation back in February, I was talking to non-astronomers, so I was giving some basics here. But it was interesting that the surface of Mars is about the equivalent of the total land area of Earth. That was kind of interesting. And temperature. But the thing about Mars, of course, it's got that very thin atmosphere. And it has lots of water, and form of ice and mineral bound water. So in terms of missions to Mars, there's been several landers. The ones in white are no longer active. The two that are still currently active, Perseverance and Curiosity, is still going strong. The first two that occurred was, of course, Viking 1 and 2. And the other thing is, there's, as far as I know, at least back in February, there were 7 active orbiters around Mars. I was going to check to see if that's still true, but back in February we had 7, and with 2 functioning surface rovers. So in terms of the Mars soil, it is influenced by wind, water, and ice. Impact, ionization, radiation, both solar and cosmic. And there's this thing called brine-driven weathering. So they have discovered probably on much of the surface of Mars or under the immediate surface, there's this dura crust, this hard layer of material. And what they think is that the water that is there, and this, we're talking about the very thin layers of water on the particles, probably with depth, is bringing these salts up to the surface, and they're forming these crusts on or under the surface of the planet. And all have seen pictures of the surface of Mars showing what appears to be old riverbeds, and we know from all the evidence that Mars has had a watery history in the past. So just some basic things about the surface of Mars. The soils are basaltic in nature, so volcanic type of material, chemically consistent globally. Some major silicate phases. These are just the various minerals, hydroclase, olivine, pyroxene. These are things we find on Earth as well, and other minor minerals. There's glass amorphous fractions. Now this is important. Reactive oxygen species, hydrogen peroxide, superoxide, particularly perchloride, is on the surface of Mars. And perchloride is extremely toxic to living organisms, and it destroys organic matter. So, surface of Mars may not be very friendly if we go there. They're going to have to deal with this stuff somehow if they're going to establish a base on Mars.
Is that the kind of material that they were thinking about using for fuel, to make fuel?
Alright.
Is that the source for potential for?
Probably go after the ice.
Okay, and then make hydrogen for water. Yes.
Sulfates and bicarbonate, some of these are important because many of these things would not exist if it wasn't an aqueous environment at one time. Lots of clays, silicates, hydrated secondary minerals, of course, iron oxides, nice orange color. Now, we were disappointed, but they found very little organic carbon in the surface of Mars. And as I talked about earlier, there's these soil crusts that have formed, which you think is the deposition of salts, calcium salts and magnesium salts being brought up near the surface. Now, of course, we know about the storms on Mars. They can have global dust storms occurring once every roughly 3 Martian years. They can last for weeks and up to months. And this is the one that occurred in 2001. And that's probably why the chemistry of the surface of Mars is fairly uniform across the planet, because of these dust storms. And these, when we say dust storms, they're hardly worth talking about because they're only about 100 kilometers an hour. Which for Lethbridge is hardly a storm, is it? Yeah. But anyway,
It's just that
anyway,
it's fine.
but it's very fine material and the gravity is much lower. So
And there's almost no air, so the wind isn't all that strong.
that's right. Yeah. Okay, just to run down here, finish off here. Perseverance is actually collecting soil samples. Well, not really. It's collecting some soil samples, mainly collecting rock samples. It's got these sample tubes, and they have 38 on board. 25 have been used. One with an air sample, 2 with soil samples, and the rest we've got 22 samples, the rock samples they've got. And I believe 10 of them have already been deposited on the surface of the planet for later pickup at some point in the future. We don't know if that's going to happen. But they're actively collecting samples that will, we hope, to be returned back to Earth at some point in the future. So weathering and atmospheric bodies, okay, so location, surface type, time, but of course atmosphere and climate, and whether or not you have a magnetic field. Earth has a magnetic field, whereas Mars does not. And that, of course, affects the effects of radiation, so. Okay, finally, just talk about exoplanets. We just, of course, I've just talked about the solar system, the terrestrial bodies, planets and asteroids. But of course, we're starting to discover planets all over the place, at least in our neck of the galaxy. And so far, they have confirmed nearly 6,000 exoplanets and then over 4,000 planetary systems. That was an earlier this month. And that's the furthest one out would be almost from here to what's that distance? That's about is it 25,000 light years, I think it is.
Mhm.
Something like that. So that's the kind of the volume that they've been able to detect planets in so far. So, of course, you know, what are the planetary surfaces are like? We know many of them are giant, large Jupiters. I mean, these gaseous type planets, but they're starting to discover what they think are terrestrial type planets, maybe large Earths or almost getting down to Earth-sized exoplanets. So, what kind of surface do they have? Do they have atmosphere on, and what kind of soil type material will be forming on that? So, anyway, soil in space. Is there soil on the moon? So, anyway.